Okay, in chapter 10, we're going to talk about moment of inertia, which is a property of materials that we're not really going to use in statics, but we want to learn about it so that you can use it later on in other classes. So let's try to develop this a little bit. So if you look at a situation where you have, say, a pool of water, like I'm trying to represent here, and the brown circle-ish, I tried to make an irregular shape, but this brown irregular shape over here is like maybe a window or something into a pool. And let's say it's a big window, so it's 20 meters deep, or it doesn't even have to be. Any depth is fine, because really what I'm trying to show here is that the pressure on the surface of this window varies as a function of y. So the pressure, let's use a different color, the pressure equals some gamma y, where gamma, as usual, is the specific weight, which is weight per volume of material, and that's the specific weight of the water. And y is the distance in the y direction here. Y is going in this way. So the deeper you go, the more pressure it is, and it's not a uniform distribution. It's a non-uniform distribution, but it's a linear distribution. For example, if you're at 20 meters depth, or 33 feet, somewhere around there, that's 1 atmosphere addition of pressure down at this point. Well, if we look at a differential area, this red thing is pointing at a differential area here between these two lines. We can then claim that we have a differential force applied on this differential area based on that, and our differential force equals pressure times our differential area, because pressure is force divided by area, and that is gamma y. Just going to replace that with what I've done up here, gamma y dA. So what's interesting is we have a differential force which is a function of y. Okay, well, the moment of this differential force about the x-axis then can be calculated simply as y, the distance y, times df. So let's substitute some of this. This equals our differential moment due to this. Let's substitute some of this other stuff back in here. So this is essentially y times the differential force, which we could represent by gamma times y times dA. Or in other words, gamma y squared dA. So if I integrate this differential moment, essentially I'm summing all the moments of all the differential areas on this piece here. I'll get the total moment, and this equals, we can pull gamma out here. I can integrate this other side of y squared dA. So assuming that gamma is a constant, which we will do. There isn't a difference in salinity or anything in the water. It's all just homogeneous water. Well, this integral here we can call the second moment of area. You might hear it called this in your other science classes. Second moment area about, or the second moment of the area about the x-axis, the way I have it, integral y squared dA, based on what I have drawn up there. And we engineers, we typically call this integral here, excluding this gamma term, just the integral, we call this the moment of inertia. And that's not really overly accurate name for this, because normally inertia is associated with a mass. So if you're doing these calculations for mass, moment of inertia is more appropriate, but everybody still calls this geometric integral moment of inertia. So in other words, if I were to draw just a general shape and select an elemental area out of this, it would have some distance y to the x-axis here, and likewise some distance, we could figure out its position, some distance x here. So I can figure out then the moment of inertia of dA. And now let's do first about x is just simply dIx. That's often what we refer to as the moment of inertia. About x, y squared dA. And about y, the y-axis, we'll get dIy equals x squared dA. So the moment of inertia of x about the y-axis, Ix, and well, about of A about the y-axis, and of dA about the x-axis. So notice this. Then, actually, before we do that, let's write this in integral form. Ix equals the integral of a y squared dA, and Iy then is the integral of x squared dA. So this is then the moment of inertia of the area about, so I summed all these up, the area about the x-axis so moment of about the x-axis and about the y-axis then. So now notice that Ix plus Iy, if I were to do this, equals the integral about a of y squared dA plus the integral x squared dA will equal the integral about a of y squared plus x squared dA. Well, if we think about triangles, if we square this side, we square this side, we get the square of this side. So this then equals the integral of r squared dA, and we call this polar moment of inertia. And again, it's equal to Ix plus Iy. And that would be represented by, let's just do a line, by this distance here, r from the pole 0, 0. You could also say that's the moment of inertia about the z-axis. All of these moments of inertia are positive. Always. All right, so let's now consider this shape here. It's rectangular shape with a height h and a base b. Doesn't have to be smaller and taller like this, but just happens to be. That's the centroid there. So if I wanted to find Ix, then what I would do is I would investigate this at some dy, differential element dy. Now I will work this out. Ix equals the integral of y squared dA. So this is so I can figure out what my dA is. This is y squared. So dA is this rectangle, and it has a width of dy and a length of b. So I can replace this by b dA, b dy, I mean. And now I've got an integral that I can solve. And we then are going to solve this as y goes from minus h over 2 to h over 2. So from the bottom, this bottom corner to the top corner here, we're going to sum up all those rectangles and find the integral of that. So this equals, well, we pull the b out, the integral of minus h over 2 to h over 2 of y squared dy, which equals b times y cubed over 3, evaluated from minus h over 2 to h over 2. And this equals b times h cubed over 8 minus a negative h cubed over 8. And that's all divided by 3. And this turns into b h cubed over 12.